Everything, air, water, fire, earth, and all living beings, are made up of a multitude of infinitesimal particles, atoms. For decades, the atom was believed to be the final term in the division of matter. In the 20th century, physicists discovered that the atom is also a world in itself.
Too tiny to be seen, atoms and the world they contain must be studied indirectly. In 1911, Rutherford, bombarding a gold leaf with a beam of helium nuclei emitted by a radioactive source, observed that these particles penetrated the material as if it didn't exist, except for the rare particles, one in several thousand, which ricocheted as if from some kind of very hard object. These collisions signaled the existence of an invisible obstacle in the core of the atoms, the nucleus. Their small number meant that the nucleus was minuscule. This experiment led physicists to propose models in which the atom consists of electrons orbiting around a central nucleus 10,000 times smaller. We've known since 1932 that the nucleus is composed of an assembly of particles strongly bound together, protons and neutrons. Our understanding of the subatomic world has steadily advanced throughout the 20th century. Yet still today, the nucleus raises many basic questions to which physicists seek answers relentlessly and passionately. How do quarks and gluons form protons and neutrons? Which fields exert their forces in the nucleus? How does each particle making up the nucleus contribute to its cohesion? What's the structure of these small quantum objects? Their shape? What are the heaviest elements? What's the boiling point of nuclear matter? What's the state of matter at extreme temperatures and pressures? How are the elements formed in the universe? How can our knowledge of the nucleus help us to understand supernovae, neutron stars, and other celestial objects?
At GANIL, to investigate the atomic nucleus, physicists bombard it with other atomic nuclei hurled at tremendous speed.
How are nuclei accelerated to form a beam? Today we know how to act on any electrically charged particle. Nuclei carry a positive charge, but this charge is neutralized by the electrons in the atom. Hence the number of electrons must be reduced to obtain charged atoms called ions. They can then be accelerated by electric fields and guided by magnetic fields. Since anything at all can disturb the ions' flight, they must travel in a very high vacuum. The GANIL accelerator consists of several cyclotrons whose magnets maintain the ions on circular trajectories. By a multitude of small electrical accelerations, the ions ultimately reach half the speed of light. The ion beam, thus produced, accelerated, calibrated and aligned, is led into the experimental areas to bombard a target foil. A collision between a projectile nucleus and a target nucleus causes the emission of radiations and fragments. Specific instruments detect these emissions, generating electrical signals. These signals are digitally recorded for detailed analysis. Like Rutherford, physicists accordingly observe the collisions induced and use the data to explore the physical properties of the nucleus. In this way they can probe, excite, deform, rotate, heat or explore a nucleus, and even create new nuclear species. Although GANIL's most intense beam corresponds to 30,000 billion particles per second, an experiment must nonetheless be run over several days to extract from the millions of collisions those which offer new information. In the data acquisition rooms, physicists work in shifts day and night to be sure that the experiment proceeds smoothly. When the accelerators are in operation, strict safety and radiation protection rules are enforced. The zones where the beam travels, surrounded by a concrete shielding, are made inaccessible. A team of engineers and technicians run the accelerator continuously from the control room.
From experiment to experiment, from confirmation to discovery, an enriched concept of the atomic nucleus is gradually emerging.
More than 100 nuclei have been discovered so far. Hundreds of others have been investigated for the first time. This exploration reveals new forms of cohesion, new stabilities, new structures. Nuclei whose predicted existence has been experimentally disproved, unforeseen deformations, nuclei surrounded by a dilute neutron cloud, the halo, nuclei resembling molecules, new magic nuclei like tin-100 and nickel-48. Vibrations of surprising harmony have been discovered, demonstrating that the nucleus possesses exceptional mechanical properties. Extreme temperatures have been reached, over 100 billion degrees. Above a certain energy threshold, the nucleus explodes and vaporizes. These studies are an integral part of the conceptual progress of physics because they apply contemporary theories like quantum mechanics, chaos, and cosmology. Thanks to the synergy of knowledge and know-how, the laboratory is at the service of other sciences and industry. Thus, basic understanding of the dynamics of atomic electron shells, on the structure of materials and on radiation damage has been acquired at CIRIL, the Interdisciplinary Laser Ion Research Center. The Ion Matter Interaction Studies Center built around GANIL is also being steadily enriched with new applications. Simulation of the aging of materials in nuclear reactors or in space. Investigations on nuclear waste incineration, radiobiology, medical applications. The construction of research facilities raises new technological challenges, a fountain of progress.
GANIL is a pioneering tool that's constantly evolving to meet the needs of new research programs. Today, Spiral delivers beams of nuclei not existing on Earth.
Until recently, targets and beams could only consist of nuclei found in abundant supply on Earth, drastically restricting the field of investigation of nuclear physics. In fact, 90% of nuclei are short-lived and do not survive for long enough to be present on Earth. These so-called exotic nuclei thereby elude our scrutiny. Physicists can now synthesize them in the laboratory. Yet to identify the structure of these new species, they must undergo collisions before they disappear. Since they're rare and fleeting, they cannot be made into targets. The beams must therefore be created immediately after the species are produced. This is achieved by spiral. Exotic nuclei are created by splitting the nuclei of a primary stable beam by bombarding a target. Nearly 1 million incident ions are needed to create a single nucleus of a given nuclear species, so the primary beam has to be as intense as possible to maximize the production of exotic nuclei. The exotic nuclei required are extracted from the enormous variety of nuclei produced in order to assemble them into a beam. This is then propelled at nearly 1/4 of the speed of light by the SEAM accelerator and sent to the experimental areas. By using these new beams of synthetic nuclei to overcome the current limits of GANIL, physicists will accumulate new data on the thousands of nuclei present in the universe. The study of such exotic nuclei tests our present understanding of the nucleus because they have very different proportions of protons and neutrons than stable nuclei. These developments and accelerators are accompanied by a permanent renewal of detection systems developed through international cooperation by many laboratories. New accelerators and new detectors are starting up. Researchers are already looking at projects for tomorrow. The nuclear physics research program at GANIL is justified by its potential for breakthroughs and discoveries.
Research is above all the work of people motivated by the desire for knowledge, impelled by the need to understand.
The scientific community is spread all over the globe, yet it's united by a common goal. Every physicist is part of a tight network of information exchanges. Internet, joint projects, conferences, publications. Ideas and results travel fast. This permanent confrontation, the ferment of scientific debate, helps validate knowledge and encourage new investigations. In the light of the latest results, teams of physicists accordingly design experiments and submit their proposals to an advisory committee composed of international experts. Approved projects are scheduled during the following year. More than 500 researchers from laboratories throughout the world spend time at GANIL every year to prepare and conduct an experiment. During the few days that they're allocated the beam, they record billions of collisions. Back in their laboratories, they replay the experiment for months, extracting the information they seek. The results are published in specialized reviews, the same ones that reported the discoveries of the researchers and scientists who laid the foundations for nuclear research. A new page in the great library of knowledge which humankind has built up from generation to generation, the results of basic research thereby join the body of knowledge shared by all. GANIL trains and teaches dozens of postgraduate researchers and hundreds of students. Thousands of visitors are welcomed at the facility every year. Physicists, engineers and technicians respond to their eagerness to understand. GANIL also means 250 people combining their expertise and ingenuity with the tenacity of the researchers to ensure the success of the experiments and to set the stage for future developments. Thus, basic research opens the door to the future by building the theoretical foundations for tomorrow's progress. Relying on a vast network of organized, structured and rational knowledge, basic research is applied to a field that is by definition limitless: the unknown.